Welcome back everyone. Today we're starting on the last topic of the course, which is optimization. And as a prelude, we'll need to ask ourselves one very important question, and that is, what makes code fast? As we will see, the answer to that question involves a lot of hardware. So in this video, we'll do a quick review of the aspect of computer architecture that impact code performance. But first, let's resituate optimization in the compilation pipeline. Here we have the simple ahead-of-time compiler pipeline that we've seen earlier. It's a bit unrealistic because in modern compilers, optimization are very rarely done on ASTs, and ASTs is what you get from semantic analysis here. There are a few things you can do with the ASTs, maybe rewrite some language constructs in a normal form that is useful for mathematical operations, for instance, or desugar some syntax into some simpler syntax. But in general, optimization are concerned with machine code, or some sort of intermediate representation that is close to machine code. So this view here is a more realistic view. Optimization can also involve special graphs data structure used for optimization, control flow graphs and data dependency graphs. And we'll talk about this in the next video. So this pipeline here is the classical ahead-of-time compiler. And at the end of the pipeline, you get an executable that you can run on your computer. Here's another pipeline with a just-in-time compiler. In this case, we get something to run, an executable or a jar file or whatever, after the bytecode generation step here. And then, before the code is going to get executed for the first time, the just-in-time compiler compiles it to machine code. One big advantage here is that, as we'll see, the just-in-time compiler runs on the target machine and not on the developer's machine. Because of this, it is able to choose the fastest instructions for a specific CPU that the program is running on. So an example of compiler that runs like this is the .NET compiler. And maybe it is a bit smarter these days, but it used to work like this. Next, we have a profiling JET compiler. So the difference here is that instead of going directly through the just-in-time compiler, you can either go to the interpreter, which records a performance profile. And once you've gone through the interpreter and you've recorded a profile, then we can choose to optimize the code and generate fast machine code. So the optimizations are performed by a just-in-time compiler are the same as those that are done by the other pipelines, but it's also able to do something with the performance profile to make better guesses and enable more optimizations. And we'll talk about this in a further video. Now that we've seen the different pipelines and where optimization occurs, let's ask our important question. What makes program fast? And actually, what makes program slow? What takes time? Well, there are two main things that take time. And the first one is the more instructions you have, the more time it takes. And in particular, the more cycle you spend, because not all instructions take the same amount of CPU cycles. The fast instruction will take one cycle, but the slowest can take tens of cycles. And by the way, if you have a CPU that has a 4 GHz clock, that means that it can perform 4 billion cycles per second, to give you an idea. The second is memory access, and I bolded it because typically memory is a much bigger concern than instruction count. The fact that memory access is much slower than executing regular instructions, it's sometimes called the memory wall. I've included an example of how this can be relevant in practice. Say you want to implement a sorting algorithm. Now we have the merge sort algorithm, and this has O(n) log n complexity. And we have the quicksort algorithm, and this has O(n) square complexity. Yet in practice, quicksort is always faster. Why is that? Well, first of all, the worst case is where for quicksort. So the average case will be closer to O(n) log n operations. But much more importantly, quicksort has more memory locality. We'll explain what that is, but basically it jumps around in memory much less than merge sort. And as we'll see, this has a huge impact on performance. Data will be accessed at different speed depending on where it resides in memory. At the top of the memory hierarchy, you have registers. There are a few of those. For instance, on x64 there are 16 registers. They are managed manually, meaning you have to load things into them and read from them yourself. Then you have caches. Caches are managed automatically, and they cache every memory access that you make to random access memory, or RAM. It's also called main memory. Most of your process memory will live in RAM. That's where the program stack is, that's where you malloc into. Every time you read from RAM, the data around the address that you're trying to access will be cached in the 3 layers of CPU cache. Every successive layer is bigger than the previous one, but also slower. So L2 is bigger than L1, it is slower. L3 is bigger than 2, but it's slower. When you try to read from memory, you'll first try to read in the L1 cache. If it doesn't work, you'll try to read in the L2 cache, etc. And say that you find the data you seek in the L3 cache, then it will write back to the L1 and L2 cache. Faster memory tends to be more expensive to produce. At least for caches, price is not the only trade-off. To be fast, these caches need to be on the processor, and the closer they are to some other part of the processors, the faster they will be. And processor space is very precious because you want to cram a lot of gates in there. So how much cache to include is also a performance trade-off, and it's not only a financial cost trade-off. Otherwise, you would have very expensive CPU with a ton of cache, and we don't have that. The 2 bottom slices of this chart are a bit weird. They should really be one layer, and that is persistent hard drives. RAM can't save memory when it's not powered by electricity, but hard drives can. And among hard drives, you have solid-state drives, SSDs, and other hard drives which are typically magnetic hard drives. And of course, as you may know, SSD are faster. You may see that the bottom layer mentions virtual memory. Virtual memory refers to the fact that each process sees memory as though it had exclusive access to all of it, to all of your RAM. In reality, many processes live in memory at the same time. So each process actually sees a virtual memory address space, which maps to the real memory. In general, that means it maps to RAM. But if there's not enough space in RAM for all the processes, then some part of the process virtual memory could be mapped to the hard disk. And for those of you that have ever installed Linux, and you have been asked about a swap partition, that's what it is. It's for mapping virtual address space to the hard disk. Now, you could look at it as though RAM was actually a very big cache for the swap space on the hard disk, but that's not entirely correct. Memory will either live on RAM or in the swap, but not in both, so it's not a cache. So, why is this memory hierarchy relevant? Well, because of these numbers that we're going to see here. Reading from a L1 cache takes half of a nanosecond. A read from L2 takes 7 nanoseconds, so that's 14 times slower. Reading from RAM, that's 100 nanoseconds, so that's already 2000 times slower than L1. Reading from a 1 GB per second SSD will take 150 microseconds. This is 150,000 times slower than accessing RAM, and 3 million times slower than a L1 reference. Magnetic disks are even slower because they're not random access. So RAM, of course, random access memory is random access. SSDs are also random access, so that you can access any part of the memory in constant time. But disks are not like that. They have a head that reads on the disk, and the disk spins. And so when you want to read something, the head needs to be positioned above the data, and just that takes 10 milliseconds, which is about 70 times slower than reading from SSD. And both for SSD and magnetic hard disk, I just told you the cost to basically start reading the data. I didn't even tell you the cost of actually reading the data. So if you have 1 megabyte, you need to add all of these things. So as you can see, it's very important to be able to read from cache whenever possible, because reading from RAM is 200 times slower than L1 reference, and reading from SSD is 3 million times slower than L1 reference. So that's quite a big difference there. Another interesting number in this chart, and this is this one on the left, the branch mispredict. So this is an approximation of the penalty in time incurred when we encounter a condition, just like an if statement, and we fail to guess which branch, so the if part or the else part, we're going to follow. And when we do that, we lose time, and we'll explain in this video why that is. So a small warning before moving on. These numbers will change depending on your processor, of course, and they generally change as technology evolve. But it is generally true that memory is much slower than processors, and I don't expect that to change anytime soon. So here's a chart showing the number of cycles that different CPU instructions and actually different operations in general take. It's from 2016, and that's probably about the same time as the previous chart. Note that this is a logarithmic chart, so every line is 10 times the previous line. So let's point to some interesting things. First, it says that simple operations take less than one cycle. That's because of CPU architecture, and we'll talk about that. But you can mostly ignore that and think that simple operations take one cycle. Then it says that memory writes take a single cycle. How is that possible? We just said that memory access can be really slow. Well, the reason is that you can instruct the CPU to write to memory, and then you can do other things. So you give the order, and then you do other things while the order is being carried out. One potential issue with this is that when you need to write to disk or to memory, and then to read from the same location, you need to wait for the write to complete. Compilers are often able to optimize this, but not always. If you've ever heard of pointer aliasing, having to wait for writes is a big part of the issue there, and this will be covered in the next video. So you can see a few more things. Floating point math is slower than integer math. Multiplication and division is slower than addition and subtraction. Failing to predict a branch is of course more expensive than not. And otherwise you get a review of the number of the previous chart, time to access the various caches, main memory, etc. There's a lot of interesting stuff on this chart, but we unfortunately don't have the time to go through everything. So look at your leisure, but for us, we'll move on. So let's talk about the caches a little bit more. Each cache is divided in something called cache lines, and you can think of them as cache slots. So to give you a concrete example, on a recent Core i7 CPU, you have a L1 cache of 32 kilobytes with 64-byte cache lines, and the L2 cache is 256 kilobytes with 64 bytes lines. These have an associativity of 8, and we'll describe what that is. Whenever RAM is accessed, a 64-byte aligned chunk of memory is pulled into the cache. What does it mean to be 64-byte aligned? It means that the address is a multiple of 64 bytes, so 0, 64, 128, etc. So when you access a memory location, you want to know in which cache line to look, the index of the cache line. You get that with the following formula. So you take the address, you do modulo the size of the cache, and then you do a truncating integer division by 64. So say the address is 129. The cache size is 32 kilobytes, so we're fine. So this is 129. And then we do a division by 64, truncating, and the result is 1. So 1 is actually the second cache line, because the first cache line would be 0. So one way people sometimes think about cache is say, well, the cache is 32 kilobytes, so it must contain the 34 kilobyte most recently accessed memory, or at least the 64 byte chunks most recently accessed. It's not how it works. And that is because of cache conflict. You see, if you access addresses, they can map to the same cache line index, okay? For instance, if you have an address that is 1 or 129, they will map to the cache line 1, okay? And that's because they're both 1 plus a multiple of 64. This is annoying because it means that if you have code that deals with an address that is maybe 1 and 129, they will keep conflicting for the same cache line, and so you will have to reload the memory each time you access it. So to avoid this problem, you have something called associativity. So the i7 has an associativity of 8, and what it means is that it allows up to 8 conflicts. Okay, so there are actually 8 versions of the cache line with index 1. There are 8 versions of the cache line with index 0, etc. For every index, there is 8 versions of it. The result of this is that the size of the cache, well, the total memory for every cache line index is 4 kilobytes, but you have 8 versions of it. So another way to think about it is that you have your 32 kilobyte cache is divided into 8 subcaches, and each of the subcaches have the different cache lines that they can put in there. So the number of cache lines is actually 4 kilobytes divided by 64. You'll note that we don't pay any speed cost for associativity, so it's not like we look in the first subcache and then in the second subcache, etc. All the subcaches are checked in parallel. It just takes a little bit more gates on the chip. So beside these data caches, a CPU actually has a few more caches that are very important. One of them is the instruction cache, so that's just to read the instruction that you're going to execute. And another one is the translation look-aside buffer, which is a cache that maps your virtual address space to the actual memory addresses, like we saw before. So this link here links to an article that's called What Every Programmer Should Know About Memory. I certainly don't know everything that's written in there, and I'm not convinced that every programmer necessarily should know all of it, but if you want the nitty-gritty on memory, caches, etc., this is definitely a place to go to learn that. So, we've talked about memory a great deal, but what about instructions? As we've already seen, not all instructions cost the same. They take different number of cycles, and they also varies in cost between different CPUs, even though it's the same instruction. There are two details of CPU architecture that greatly affect performance. That's memory caches, so we just talked about that, and then there's instruction pipelining. Let's now talk about this. So the basic idea of processor pipelining, which you can see on this chart on the right, is that every instruction is executed in multiple stages. So fetch means fetching the instruction, decode means understanding the instruction structure and actually converting it into the real instruction that the CPU executes, which is called microcode. It's not something we need to think about, but the CPU itself, it's an interpreter or maybe a JIT compiler that executes microcode. So how crazy is that? So you execute your microcode, that's the execute step, and then if the instruction writes to a register, you do that in the write back stage. So the idea of pipelining is that while you execute an instruction, that's the blue box, you can decode the next instruction, and you can fetch the one after that. And if you do things in this way, you will keep each stage of the pipeline busy at all times. Okay, so when you have 4 blocks here, it means that all the 4 stages are working on a different instruction. A big goal of optimization will be to keep the pipeline as busy as possible. And failure to do so is called a pipeline stall. So one thing that causes pipeline stalls is branch mispredict. So if you encounter an if statement, the CPU will try to guess which branch will be taken, and it will speculatively enqueue instruction from this branch. If it turns out that the CPU was wrong, it will cancel the instructions, and canceling the instructions is actually easy, but the problem here is that the parts of the pipelines that we're executing speculatively will be stalled, and they will be unused as we wait for the instruction from the actual correct branch to make it true. If you mispredict, you do useless work, and then when the actual instruction comes in, you need to wait, and you have some stages here that are doing nothing. So that's a pipeline stall. Another way that pipeline stall occur is when we have too much data dependency. So data dependency occurs whenever an instruction depends on the result of a previous instruction. Optimizing compilers, they will try to reorder instructions to avoid these stalls, but it's not always possible. Sometimes you just need to wait for an instruction to go through the whole pipeline before you can start on another instruction. So that is basic pipelining. There are some advanced variations in this theme, and the first is superscalar processor, which you can see on the second chart here. Superscalar processor exploit instruction-level parallelism, or ILP, to run multiple pipelines in parallel on the same CPU cores. This can be used to run multiple instructions that don't have data dependencies in parallel. You can basically think of it as having multiple pipelines on a single CPU core. There also exists some special instructions, VLIW instructions, so that's very long instruction words, and these let you emit instructions that will automatically fill these pipelines. Another variant of the processor pipeline architecture is simultaneous multithreading, or SMT, and you might know this better under Intel's name, which is hyperthreading. The idea is that since we want to avoid pipeline stall, we can fill the gaps in the pipeline with instructions from another thread or process. This is pictured here. So as you can see, you have the blue thread and the green thread, and what you have here is a superscalar processor. So in the first case, we're running 2 instructions for green thread, but we don't have a third instruction to run there. And so what we'll do is to fill this pipeline here, we'll use an instruction from the green thread instead. And you can see that play out in the different stages of the pipeline. However, there's a very big pitfall here. And that's the fact that the caches are shared between the 2 threads because they run on the same core. And potentially, this can make SMT slower than just running both threads separately without SMT. And that's because the second thread can basically pollute the cache for the first thread, greatly impacting its performance. Finally, we have single instruction multiple data, or SIMD. SIMD is not really a pipeline architecture, so there's no graphic for SIMD, but it's a capability offered by processors to exploit data level parallelism. Basically, you use SIMD instructions, and with that, you can run the same instructions on an array of values, which is also called a vector. Here I've wrote tightly packed data, but that's the same idea, it's just an array. So instead of running the instruction on a single value, you run one instruction, but will run on every value in the array. This is particularly variable for all kinds of data crunching, like image and sound processing, mathematical computing, machine learning, Bitcoin mining, whatnot. So here's a question. Is SIMD a solution to the problem that memory access cost dominates runtime cost, the memory wall? The answer is no. First, it only works for data on which you want to perform the same operation, so that's not a general solution. Second, this data has to be packed together. It has to be contiguous in memory. So even if we didn't have the SIMD instructions, it would have been fairly fast to operate on this data because it's in the same memory location, so it will be in the cache directly. SIMD just makes this even faster by making you able to process a vector at a time instead of just a value at a time. So you save a few instructions. Actually, you save as many instructions as the length of your vector. Okay, I want to mention that all the charts from these slides on pipelining are taken from this article here, which is called Modern Microprocessors, a 90 Minutes Guide. And I highly recommend it. It's very well written. And there are a few more details that I did not explain here. So, as a programmer, what can you do to improve performance? Obviously, you can select your algorithms and your data structures well. So, when you think about complexity, you should consider both the worst and average case. But beyond complexity, really consider the quantity and the pattern of memory accesses. Something that accesses memory locally and that does less memory accesses is inherently going to be faster. The second thing you can do is try to help the compiler in any way you can. So that's giving the compiler information that it would be unable to infer. To give you two maybe not that good examples, but to give you the idea, using final in Java, for variable, it means that the variable cannot be rewritten, and for methods, it means that the method can be overridden. And so typically the compiler is able to figure that out, but in case it isn't, it can reason with that and make optimization that it otherwise couldn't. Another example is storing an intermediate value in a variable instead of recomputing it. And what that says is that you just care about the result and there is no significant side effects from computing the value that needs to be repeated. So like I said, compiler typically can figure that out, but not always. So for instance, on the project that I'm working on, Truffle Ruby, we do find that sometimes final helps, even though typically it shouldn't. And this might be related to the compiler's optimization budget. Okay, so the compiler can do a lot of optimization, but we do not want it to spend all its time optimizing, because especially if you have a just-in-time compiler, that can put a lot of strain on the machine. When you say that something is final, the compiler does not need to try to figure out if it is final or not, if the variable is reaffected, etc. it can just make sure of that because you told him, and semantic analysis checked in during the compilation to bytecode. So what you really want to know in this course is how can the compiler improve performance? And I'll give you 3 main directions, and we're going to explore them in more details in the next video. So the first is improve cache utilization, which mostly comes to avoid jumping around in memory, which destroys the cache. And so basically improve cache locality is another way to say that. The second is improve processor utilization, and mostly that comes down to avoiding pipeline stalls. What optimizing compilers like to do here is reorder instructions around to make sure the pipeline is being used as much as possible. And third is remove obstacles to optimization. I'm not going to say anything about that one. We'll see that next time. So yeah, we're done with our review of the hardware aspect of performance. In the next video, we'll apply this knowledge to understand how common compiler optimizations work. Until next time, have a good time.